Okay, so yesterday we wrapped up chapter 4.2, which was electrical quantities, and today we'll be starting with 4.3, which is electric circuits. I can put that up here. So, right, obviously, when we're talking about electricity, we're going to talk about electric circuits, which are, electric circuits are various electric components joined, right, or connected together, obviously for some purpose. They obviously have a power source and they form a complete circuit, right? So it goes from point A to point B, right? It might be circular, perhaps, depending on how it's set up. And so to represent different components, right? Different components of an electric circuit, components of an electric circuit, right? There are certain standardized uh, representations of those called circuit symbols. Right now, for the circuit symbols, for the ones that we need to know, and others as well that will come later on, but for some of them, right, they're introduced at the start of this chapter, so I'll show them to you instead of having to draw them all on the whiteboard. There we are. Right, so a straight line is a connecting wire. If two wires are joined, they're shown by a solid dot at the point where they're joined. If they're just crossing, they're not connected or joined, then they're just shown as overlapping lines. This is a cell, that is a power source, right? The longer line is the positive terminal, the shorter line is the negative terminal. And it is normally made with the positive terminal on the left side and the negative terminal on the right side. If two or more cells are connected together, that is called a battery. And so it's represented by showing two of them with a dotted line in between. This is a switch. So it's a diagonal line, a thicker line showing a disconnection of the circuit. So when the switch is closed, the circuit is broken and so electricity does not flow and so nothing's happening. When the switch is closed, right, it allows electricity to flow because the circuit becomes complete. The ammeter and the voltmeter, we're familiar with those, we've come across those to measure current and voltage, right, potential difference. And so they are represented as a circle with the letters A or V inside them. Keep in mind to make them capital, so uppercase. And again, right, they're represented with the positive terminal on the left side. A lamp is a circle with a cross in it, so that is a lamp. A resistor is basically a rectangle with the wires going in and out. A variable resistor is the same with a diagonal arrow going from the lower left to the upper right. And a fuse is a rectangle with the line going all the way through it. So these are how many? These are 12 symbols, circuit symbols that we need to be familiar with. And then some that will come in later. So thermistors, light dependent resistors, relays, light emitting diodes, and semiconductor diodes. We've seen some of these, right? The thermistor and the rheostat, right? Sorry, the potential divider, not the thermistor, but the rheostat and the potential divider and the variable resistor. So we've seen symbols of them earlier on, and we'll be coming across those again later as well. So yeah, these are symbols you need to know. Now, we're going to talk about uh, circuits that are set up in series and then circuits which are set up in parallel. So let me go back. Okay. So, right, a circuit can contain many different right components. My whiteboard is lagging. Okay. And it can be set up in series or parallel. So what does series mean? Right, that the components are connected one after the other, sort of in a line, right? So you got something over here and something over here. I'm not drawing resistor, I'm just like, some component. Something over here and something over here, and then, whereas in parallel, right, the components are set up in a branched way, right? So they're set up side by side. And so they look like this. You've got one component over here, and one over here, and then one over here. And so, right, this is how they sort of are connected. Right, so it's a straight line there, side by side or, branched. Now, whichever way they are set up, what we need to figure out is, oh, okay, so if they're set up in series, and so those are terms I'll be using now, right? So just for you to keep in mind. If the circuit is set up in series or if it is set up in parallel, right? What's the current? What's the voltage or potential difference? What's the resistance? Right? How does being in series or parallel affect these three? And so the first thing we want to talk about is current in a series circuit. And so to diagrammatically represent that, oops. Huh. Okay, I don't know how this works. Oh, that's how. Okay. So that is an image of, right, a circuit set out in series. And so how do we know the current, right? The amperes. And so as you can see the arrows pointing in a series circuit, the current is the same at any point of the circuit. So whether you're at point B, C, the reason that they haven't labeled point is because you got an ammeter over here. And so if the ammeter is over here, or if it's between the two lamps, or if it's at point C or point D, anywhere the ammeter, because the ammeter measures current, and so anywhere the ammeter is placed, the value of the current will be the same. So the current is the same at any point of the circuit which is set out in series. That's what you need to know. Questions? Then you have the potential difference. Well, no, actually, current and a parallel. We're doing that first. And so let me put the image up over here for that. Hmm. Do that. Okay. So this is, right, a parallel circuit. You can see that the two lamps are set, you know, side by side. And so the current splits, right? The total current splits between the different components of the circuit, right? So the ammeter placed over here or placed at point R, right, will have the same value because this is current going in, right? This is going in and this is current coming out. But P and Q are different. If the ammeter is placed at point Q or at point P, it will give different readings because over here, right, it's giving you the total current, so total I, right, that is in the circuit. But when it reaches this junction over here, it splits. All the current does not go to the first lamp, only as much is required goes and the rest goes here, so it splits. So the explanation they've given over here is, for example, right, your supply. So the ammeter over here, for example, is reading 0.4 amperes. So that is the total supply. And there are two identical lamps. So these guys are identical. And meaning identical, that means they're going to use the same current. And so there are two of them. And so that each one of them will be using 0.2 amperes. So the ammeter connected at Q will give a reading of 0.2. The ammeter connected at P will give a reading of 0.2, right? And so 0.2 amperes comes out from each, and then over here again it's 0.4. Does that make sense?
Yes. Like the ammeter is providing the current or
Ammeter,
battery is.
the cell. A single is called a cell. Multiple cells connected together are called the battery. Like for example, over here, you've got more than one cell, so this thing is called a battery. Okay, so that's about uh, right current uh, in a parallel circuit. So if the lamps were not identical, for example, right, if one of the lamps was taking 0.3 amperes, then the other would have been taking 0.1 because the total supply is 0.4 amperes. Okay, and so basically what we can say is I equals to I1 plus I2 plus I n, n meaning whatever number of junctions there are, right? However many splits or branches of the circuit they are in parallel. The total current supplied will be split. So you take the current of each individual branch of the parallel circuit, you add them all up, and you will get the total current. Okay. Okay. Next is current at a junction. And this is basically saying what we've already mentioned. Right, so a junction is this thing, or right, these parts, right, wherever the wires are joining. And so basically the total current going into a junction equals to total current coming out, right, which you already mentioned. So it's 0.4 is coming in, it's splitting 0.2 here, 0.2 here, and then coming out the total is 0.4. So that's basically what they're trying to tell us over here. Next up is potential difference. So first of all is the potential difference in a series circuit. And since I've discovered something new today, right, let me get that snapshot. So here is, right, another series circuit. You can see you've got 3 lamps connected, a 4.5 volt supply. And so in a series circuit, right, the potential difference is split across the components. So the total potential difference of the circuit is equal to the sum of potential differences across each component of the circuit, right? So whatever potential difference is across the first lamp and then the second lamp and then the third lamp. And so the total V equals to V1 plus V2 plus however many components, in this case 3, Vn. Okay, in this case it's 3 because you've got 3 lamps, right? And so what you can guess is, for example, the first lamp, so we know V total is 4.5 volts because that's given to us, right? And V1 is 1.4 volts and V2 is 1.5 volts. And so what is V3? So we can do that. We can do 4.5 equals to 1.4 plus 1.5 plus V3. And so V3 equals to, right, you add this and you shift it and you get 1.6 volts. And so in this case, the potential difference across the 3 lamps, just to, explain the concept, they're not kept it the same. They could have said, oh, it's 1.5, 1.5, 1.5. They haven't done that. And so the total voltage coming in, each component in series is going to take whatever voltage it requires. So the potential difference across each component is going to be different, but the total voltage coming in, right, and the total voltage going out is going to be the same. Across each component, it's going to be different depending on how much voltage each component is utilizing. Make sense?
Yes. Like in a series circuit, it will be the same,
What will be the same?
like the potential difference,
Where will it be the same?
like among all the lamps
It
and.
will not be the same.
Okay.
It depends on the requirement of, in this case, it's a lamp. It could be something else, right? It depends on the requirement of the component. In a series circuit, the potential difference is split between the different components depending on their requirement. Right, so the way current behaves and the way voltage behaves is different. In a series circuit, the current is the same, but it splits in parallel. Right, potential difference in a series circuit splits according to the requirement of each and every component. Now you can imagine, perhaps you can guess how potential difference will behave, right, in a parallel circuit. Let me get a snapshot of that as well. Whoops. Okay. All right, so this is a circuit that has 2 lamps in parallel, right? And you've got 2 voltmeters over here, V1 and V2, and this whole thing is connected to a 1.5 volt cell, right? So the current is coming in from here, right? And from here, I mean the voltage, I should say, in this because we're talking about the potential difference. And from here it's splitting, and right, it's also going here and here. So there's 4 places it's going, and from everywhere, right, it's going to come back and then do the round. So in a parallel circuit, the potential difference is same across all junctions. Okay, so
Yes.
right, so in this case V1 equals to V2, right, equals to V, the total. So you're going to get 1.5 volts over here, you're going to get 1.5 volts over here. It's going to be the same across all junctions. So that's simple, right? If you've got a parallel circuit and they're going to ask you what's the potential difference across each junction, or this particular junction, or this particular component is the same as the supply coming in. Okay, so that's simple enough. Okay, now, right, cells, batteries, and EMF. Now we know a cell is a power source given this way, right? This is positive, this is negative. And if you connect multiple of these guys, so there are two ways you can connect them, right? You can either connect them in series or you can connect them in parallel. And so, right, what's the effect? And also, right, positive to negative to positive negative. So, right, why? Because you're going to keep the flow in one direction, right, going from positive to negative. So what's going to happen with batteries in, right, series? The EMF adds up, right? So if each cell is 1.5 volts and you've got three of them, right? So that's 1.5 plus 1.5 plus 1.5, and that's going to give you 4.5 volts. But in parallel, right, they don't add up, they remain the same. So you've got 1.5 here, 1.5 here, 1.5 here. The total voltage or EMF is 1.5 volts. So what's the point, right? Then why do I have three cells? Why do I have this battery with three cells connected in parallel if they're only going to give me 1.5 volts? Well, you've got, they're going to last you longer, right? Because the supply that you need is only 1.5 volts, but instead of using a single cell, you're using three cells, and so it's going to give you that EMF for a longer period of time because there are three of them as compared to having only one. So that is a difference, right? When you're using a device and you see sometimes, right, the slot is long where you need to insert your cells and you can add like, three of them. That means it needs more EMF. And so those in series, right, the voltage adds up. Whereas you've got this kind of arrangement where they're in parallel, right? And that means you're getting the same, but it's going to last for longer. Also, if, right, your batteries are not in the correct order, right? So you've not connected them positive to negative, but you connected them like this, right? So this is positive negative, and then you connect them to positive to, like, negative to positive. And so they're going to cancel each other out. And so in this case, right, your potential difference is 0, right? There's no current that's going to flow. All right. Okay. Any questions?
No.
Okay. Now they mention over here that when a battery is being used, its potential difference decreases slightly, and that is due to internal resistance. When a battery is not being used, it gives its full, potential difference. That's something mentioned over there. And right, they also remind us of the equation that voltage equals to, right, work done per unit charge. That's something we've done earlier, and it's reminding us that, oh, remember we talked about that? Just keep that in mind. Shall we continue? Yes? No?
Yeah. Yeah.
Okay. So we've talked about current, we've talked about voltage. So what do you think is coming up next?
Resistance.
Resistors. Good. And so now we're going to talk about resistors in series. So let me get the snapshot for this. I feel like I've, unlocked like a special skill or something. It is making life easier. So here we have a circuit with resistors connected in series, right? So we got R1, R2, R3. Because they're in series, we just learned that the potential difference across each one of them is going to be different as the resistor requires. And the total voltage, right, is going to be V1 plus V2 plus V3. Because they're in series, the current going in and the current coming out is the same. So keep the things that we've learned in mind. So how do we get the total resistance?
Resistors provide resistance.
Yes. I mean, the conducting material, the wire and whatever has its own resistance, but if you want to increase the resistance of the circuit, for example, to control the volume, for example, in a TV, right? There used to be knobs earlier, now it's digital, but they work using resistors. So I'm guessing the higher the resistance, the lower the volume. When you increase the volume, you are lowering the resistance, and so that gives you more sound, right? And so that's why you purposely add resistors to circuits for specific purposes. Now, what we have over here is, right, we're going to use voltage to figure out how to, get the total resistance of a, when they connect in series. So V equals to IR, right? And for each individual case, right, the current is the same. Remember that, right? Current is not changing in series. The voltage is changing. So V1 equals to I and whatever the resistance is. And V2 equals to I and R2, and V3 equals to I and R3. And so V equals to V1 plus V2 plus V3. So we substitute all of that. So we get IR, that's the total voltage, equals to IR1 plus IR2 plus IR3, right? So this is total voltage. or total potential difference, and this is total resistance of the circuit, right? And the current is the same. So what we're doing over here, we're doing IR equals to, you take I common, and you take R1 plus R2 plus R3, a bit of math, right? These guys cancel out, and so what you get at the end is the total resistance equals to the sum of resistance, right? So the total resistance in a,
And
huh?
and if we have to find the current, then we are gonna take R common.
Well, I mean, yes, if the current is unknown and you're given the values of V1 and R1 and all of that, then obviously, right, you can manipulate this and you just input the values of R and then get I, right? So that obviously mathematical manipulation is there, right? But
Yes.
just as far as the understanding goes, the total resistance, right, when they're connected series, is the sum, is equal to the sum of the individual resistances. Okay.
Yes.
Now we talk about resistors in parallel. We have an illustration for this that I can use. Yes, we do. And so this is an interesting one, right? We need to follow along a bit for this one. So what we're doing here is we know that, right, V in equals to V out, right? The voltage going in is the same across all junctions because it's in parallel. Current, on the other hand, is the sum of individual currents, right? So we already talked about that. And so V equals to IR, and so I equals to V over R, right? I is the one being split. And so when you got I1, I2, I3, right? You have V over R1 plus V, in this case, you got three of these guys, V over R2, right? And V over R3. Now, right, as many resistances as there are, it's going to get complicated. So what we're going to do is just going to talk about, oh, let's say there are only two of them, right? So only two resistors. And so we've got V over R equals to V over R1 plus V over R2. Right? And you see, and you take V common over here. And so what you're left with is 1 over R, that's not I, equals to 1 over R1 plus 1 over R2. Right? Then you do the math. So you take an LCM. So 1 over R equals to, you got R1 plus R2 over here. Sorry, R1 times R2. And you got R2 plus R1 over here. Right? And then you, right, take an inverse of both sides. So you get R equals to R1, R2 over R1 plus R2. And that's how you figure out the total resistance in a circuit in parallel, right? So R total equals to product of resistances, so that's multiplication, over sum of resistances. Make sense?
Yes.
Right? And so what that tells us is the combined, right? So this is something we need to remember. The combined resistance of two resistors in parallel is lower than, right, is less than the resistance of either, the individual resistors. It's less than the resistance of the individual resistors. So, right, there are 2 points of summary for parallel circuits, and then we can perhaps do a few numericals, and that's actually the completion of like chapter 4.3.2 as well. Oh, did I just cover? Just a sec. Oh, okay, the first part was only the circuit symbols. So, properties of parallel circuits. Right, the first property is that the current from the source is larger than the current in each branch. Why? Because the current splits. And the second is, we just saw that, right, that the combined resistance, now the book says 2, right, but however many is less than each individual resistance. And the third, they've not given that, but the potential difference across each branch is the same as the source, right? So the voltage is not split. And so they give an example of lamps that are connected in parallel. And so the advantages of lamps being connected in parallel is so that they all get the same voltage, and so they all shine with the same brightness. If you connected the lamps in series, then they would utilize the potential difference, and so with each successive lamp they would get dimmer and dimmer because they're getting less and less voltage. But if you connect them in parallel, they're all getting the same voltage, right? And so they're all lighting up as brightly as the next one. And the second advantage is, because they are in, right, the advantage of parallel circuits is in parallel circuits, right? Components, each component is independent of the other, right? So if any one component, like for example, resistor 2, it stopped working. Resistor 1 and resistor 3 will still keep working, right? Because the current is being split, the voltage is the same, and so it's not going to affect the other resistors in the circuit. Whereas over here, if resistor 2 stopped working, right, the circuit will stop working because it's not flowing, right? The current will stop flowing through the whole thing, right? And it's not passing, and so the whole circuit will shut down, right? Worst case scenario. Otherwise, simply, you know, it will only work up till resistor 1 perhaps, and then, you know, resistor 2 and resistor 3 won't work. So it's going to affect the components that come later on. But otherwise, it's going to cause your circuit to shut down. So there is an advantage in when for parallel circuits, unless your focus is supplying the same current, in which case you would want to connect your components in series, because in series the current going in is the same as the current going out. It is not split. Okay, I'll stop over here. We'll come back after a break and then we'll do some numericals and then move ahead. All right?
Okay.
All right. See you in a bit.
Allah Hafiz.
Allah Hafiz.